Then once the steel is determined, then you need to know the type of connection. If you are using a bolted connection for your area, you have to determine the effective area of the section, and the effective area is section is equal to the gross area minus the area due to the hole. The formula for the area due to the hole is given in the code. You can check that out. But because you are dealing with a welded connection, there is no hole created, so you can just multiply the area of your section by the strength of your steel. Hi guys, this is Chef Jin Academy once again. In today's video, we are going to be looking at the second part of truss design. So in the last video that I uploaded on YouTube, I've already discussed the bar where we actually classify the truss section, and then we determine the parameters from the steel table. So in this part, you are going to be looking at the design or the check required for us to be able to check for the adequacy of this truss roof system. So all you have to do in checking for this is to check for the capacity of the section peaked against the imposed load. The section that was peaked was a L section, equal angle of 50 by 50 by 6. So all you just have to do is you check the capacity of this section against the load imposed. So it's as simple as that. For those of you that have not watched the first part of this truss design, you can check the description of this video. I put a link to the video where you can watch it for free. Don't forget to subscribe to this channel, because doing so is going to assist a lot of people in getting this video to get notification for all the videos I make in the future. I know you enjoy them. So thank you. Let us now get into this part. So in our previous class, we've tried to classify our steel section. So, and at the end of the classification, we arrived at a section that the section is semi-compact. There is a particular reason why we are going through this classification process. The reason is because you have, our member is either a compression member or a tension member. So if it's a compression member, due to the effect of the compression on the member, then this tends to reduce the effective area of the section. So in that kind of situation, you need to know, because the code already specified for different classification, there is a different formula for calculating the area. I'm going to show you the formula for doing that later in the class. So once you classify your section to either plastic, compact, semi-compact, and slender, so depending on the classification, they know the formula to use for your area of section. Then the same thing applies to tensile forces. When tension is applied to a member, when tension is applied to a member, what happens is it tends to elongate. It tends to increase in size. That is the norms. But for example, now let's say we now have holes. Like when we want to provide connection design, we provide a bolted connection. When we provide a bolted connection, when the member is stressed under tension, what will happen to those holes? Those holes will tend to enlarge. So that's why in calculation for in designing for a tensile member, we need to consider the effective area due to the hole. You need to reduce the area of the hole from the area of the section, so that the area of the hole tends to reduce the effective area of the section. I hope you get. So that's when the idea of effective area comes to play. So to now continue with the class, we just have only two more steps to take, and the two steps just include the design for the compressive member and the design for the tensile member, since we've classified it. So to design for the compressive member, you need to determine the effective length. How do you get the effective length? You need to go to table 22 of the code. So let's quickly do that. This is the code. This is table 22 of the code. You see what you have here is notional effective length for a compression member. This is usually done for compression members. So you first of all need to classify your member as either restrained or unrestrained. But when you are dealing with a frame like this, like a truss like this, you can just work with non-restrained in direction in either end. Just work with this direction and pick an effective length of 0.1. But let's say your truss member is restrained. Maybe there is something at the top of it, or it's kind of restrained, maybe by wall or by anything. That you can pick any other type of end condition. But most times when the two end of the member is fixed, then that's when you use 0.7 multiplied by the length. But when one of the member is pinned and one is fixed, that is when you use 0.85. But when you have pin, but in our truss design, we assume that the joints between these trusses are pinned. So that's why we are using 1.0 times the length of the section. So that means our effective length is going to be 1.0 times length. And for our compression member, if you can recall, the length of our compression member is 0.6. Let's still use our blue color. The length of our compression member is 0.6. That means our effective length is 1.0 L. So this will give us 1.0 times 0.6. So this is gonna be 0.6 meters. 0.6 meters. Then you need the radius of gyration. We've calculated this. So I think what we got was what we got for the radius of gyration was 15 mm. So 15 mm. So that means we have 15 mm here. 15 mm. So once you now get the effective length and the radius of gyration, you can now determine this lambda. This lambda is known as the slenderness ratio. So this slenderness ratio determines a lot of things. It is what you use to determine the compressive strength of the section. So the slenderness ratio is equal to the effective length over the radius of gyration about the y. So that means we have 600 if you convert 0.6 to mm divided by 15. So that will give us a slenderness ratio of let's quickly use the calculator. So you have 600 divided by 15, you have 40. So that means the slenderness ratio is 40. So this slenderness ratio will be used together with table 23 to determine the compressive strength of the member. So let's now head over to table 27 and see what is there. So this table 27 will give us the curve that we are going to use to determine the compressive strength. The compressive strength depends on the lambda and the curve that we obtain from table 23. So let's go to table 23. This is table 22. So that means table 23 is a little bit down. So this is table 23. So now we need to look for our own section. Our own section was a road angle section, equal angle. This is what we are using. So when you are dealing with a road angle section, then you use any axis C. So that means our axis of buckling, we are going to use the curve C. But let's say you are dealing with an I section. So if your thickness is less than 40 mm, then along the x-axis use this, then along the y-axis use this for the curve. When the thickness is greater than 40 mm, I think it's just easy to work with this table. Just pick the section that you want, then look at the curve, then determine the axis of buckling. So you need to know which curve. We have 3 curves, A, B, C. But for angle section, channel section, and T section, you only use the curve C. So let's now head over to curve C. So that means from here now, our buckling allocation of strut curve is C. Our buckling allocation of strut curve is C. So we now need to go to the next table, which is table 24. Under table 24, we look for curve C, where you have curve C, and then determine the compressive strength. So you just have to come back to the code and just go to table 24. So this is table 24 here. You can see compressive strength PC in Newton per mm square. So they now say when the value of compressive strength when lambda is less than 110 for strut curve A. Our own strut curve is C. So we look for the one with strut curve C. This is strut curve B. This is strut curve B. Then this is our own strut curve C. So you cannot see here we have lambda, you have the design strength, you have, so when your strength is 275, this is what you use. When your strength is 375, when your steel grade is 275, 375 and 460. So depending on the steel grade, then this is now the strength. When we classify our member, the strength was 275, so that means we'll be looking under 275. Then what is our lambda? Our lambda was 40, so this is 40. Then we read it against 275, so that means the compressive strength of this section is going to be 238 Newton per mm square. I hope you understand that simple logic. So come back here now. So that means our compressive strength is 238. Simple as that. But the value is in what? Newton per mm square. So once you determine the compressive strength, we already know the compressive force that is acting on the member. The compressive force acting on the member from our analysis was 13.2 kilonewton. So what we just want to do is we want to know if the compressive force that is in which the member can take is up to the compressive force coming on it. So if the compressive force coming on this section is less than the compressive strength of the member, then that means the section is okay. That's just the steel design is no more than that. You just compare. You compare the forces. Compare, okay, this forces is coming, okay, and this is the forces that we have that the member that our section can take. You compare the two. If it is less than what your section that can take, that means you need to pick another section. If it is greater than what your section can take, then I hope you understand that logic now. When it is greater than what your section can take, you pick another section. When it is less than what your section can take, you use that section. That's just the logic behind it. So you now need to determine your compressive force. What is your compressive force? Your compressive force, PC, is equals to strength times area. This is just a fundamental formula. It is not written anywhere in the code. It's a fundamental formula that force is strength times area. So we already know our strength as 238. Then our area, we've determined the area of the section. But to know the formula to use, the compressive force to use, this was actually given in the code. If you go back to table 22, if you go back up, not sure, okay, if you come to this table 22 where we calculate the effective length, if you look down, you see compression resistance. So you see you have two formulas. The first formula is for class 1, class 2 and class 3. The cross-sectional area, the compressive force is AG times PC. AG is the area of the section. So you get the area of the section is AG times, you can see AG is the cross-sectional area, the cross-sectional area of the section, and that is what we obtained from the section table. So then you just multiply by the strength. But if after classification your member falls on class 4, that is a slenderness section, you need to determine the A effective. So the A formula for the A effective is given in plus 3.6. So you can check that out if your member is slender, but our own member isn't slender, so we work with. So that means you are going to use this formula straight up. So that means from here now, so we need to determine the AG. We've obtained that earlier. So area of our section was 568 mm square. So you just multiply this guy by 568. So you multiply 238 by 568. So this is going to give us a very big number. So that is 238 multiplied by 568. So this answer is in what? This answer is in Newton. So to convert it to kilonewton, you divide it by 1000. So that means we have 135.4. 135.4 kilonewton. So now we know that to now know if our member is okay, 135.4 is greater than 13.2, which is the compression member, compressive force, kilonewton. So that means section is okay. that means section is okay. So that means the compressive for the compressive member, for any member that is in compression, section 50 by 50 by 6 we take the forces effectively. So let's now go for the tensile force. To determine for the tensile force, the tensile member design is very, very easy. The only thing that is a little bit hard there is the area, and I've explained the area when you are using a bolted connection. When you are using a bolted connection, in that kind of situation, you need to reduce the area of both, the area of the hole. Sorry, for you to put a bolt connection, you make hole on the section. When you make hole on the section, this will reduce the gross area. Get. So you now need to calculate the effective area of the section. So the effective area of the section, there's a formula for that, but let me just see if I can find where that is in the code. So if you come to clause 4.6 of the code, you see tension member. So you see tension capacity. So you see the tension capacity is equals to PT times PYAE. So you can go through this stuff. You can see that for bolted connection you have this formula, for welded connection you have this formula. The reason why you have this formula for welded connection is because sometimes you can have combination of bolt and weld. It's not that most times you don't just use one connection, depending on the type of project. So but in this situation we are using welding connection majorly, so there is no hole provided in the section. So that is why the formula for the design strength is just going to be the strength of the steel multiplied by the area, and that's all. So that means now, so how do you now get our tensile strength? Our tensile strength is equal to the strength of our steel. During the classification of the steel, we know that the thickness was less than 16 mm, and therefore the strength of the steel is 275. So that means the strength of our steel is 275 Newton per mm squared. That is the strength. So it's simple as that. Then you don't need to get the tensile force. The tensile force is just the same thing, strength times area. If there is hole, you need to reduce the effective area. You need to reduce the effect of the hole in the section. But in our own case, we are doing a welded connection, so there is no hole. So that means our tensile force is going to be 275 multiplied by the area. The area is 568. So this is also going to give us a very big value. That is 275 multiplied by 568. Sorry, 568. So this one gives us 156. If you divide it by 1000 to convert to kilonewton, you have 156 kilonewton. And 156 kilonewton is greater than the maximum tensile force coming on the member was 30.75. So that means 156 is greater than 30.75. So that means 50 by 50 by 6, 50 by 50 by 6 section, angle section is okay for this design, even more than okay. I hope you get. So then I forgot to tell you something. In determination of your compressive force, in that table 24 that we use, let's assume that your slenderness ratio was not in that list. Like let's say instead of 40 that you get something like 39. But in that list you can't find 39. You can just interpolate between 35 and 40. I hope you get. So that means your section of 50 by 50 by 6 is okay for the member, either the tensile forces or the compression members that are subjected to any of those effective forces. So that is how to go about the manual check of any truss design. So with this information, with these few steps, the first steps is you determine the section data of the section. Once you determine the section data, then you classify the section either class 1, 2, 3, 4. That is plastic, compact, semi-compact, and slender. Once you determine them, then you now design for the compressive member. To design for the compressive member, you get the effective length from table 22. Then you obtain your radius of gyration about the y-axis. Then you get your slenderness ratio. Once you get your slenderness ratio, then you go to table 23. get the buckling allocation strut curve, that is the axis of buckling. Then from there you determine your compressive strength, then you determine your compressive forces, then you compare the compressive force with the force that is acting on the member, with the compressive force acting on the member. Then for step 4, you determine the design for the tensile member. You just need to determine the strength of the steel. The strength of the steel depends on the thickness of the steel. Once you get the thickness and you know the steel grade that you want to use, you can use table 9 to determine the strength of your steel. Then once the steel is determined, then you need to know the type of connection. If you are using a bolted connection, for your area, you have to determine the effective area of the section. And the effective area of the section is equal to the gross area minus the area due to the hole. The formula for the area due to the hole is given in the code. You can check that out. But because you are dealing with a welded connection, there is no hole created. So you can just multiply the area of your section by the strength of your steel. Then once you get the strength of your steel, you compare it with the tensile force coming on the member. So if it is greater than that tensile force, that means the section design is okay. So that is all about the manual design for strut members. So see you in the next one.